Okay, this week I want to discuss these 4 things. Today's lecture is divided into 4. We will finish up process management. Remember last week when we started, I told you there's a second part which we will do this week. Then we'll do process synchronization. We'll look at inter-process communication, that is IPC. And then we'll finish up by looking at concurrency of processes. And specifically, we will look at deadlock and starvation. And that will be the end of the lecture. So it's divided into the 4 sections. So allow me to start. The first part, I'm looking at process management. And I hope we still remember what we discussed last week because it's a continuation of the same. But I'll do a brief recap. Last week we said if you open the task manager, specifically on Windows, it allows you to see the processes on programs that are active. And we defined a process as a program in execution. And I remember giving you the example of if you have Microsoft Word open, the moment it is executing, it becomes a process. And within Microsoft Word program, you can have as many processes as possible. For instance, you can have one process correcting your grammar and error and spelling mistakes. You can have another one maybe printing in the background if you've sent something for printing. You can have another one maybe checking on other things that you're doing on your Microsoft Word. So ideally, the key thing here is that when you have a program, it can have many processes attached to it. So on the right of our screen, on the screenshot that I have, on the left, sorry, these are the applications or programs that are running in this particular system. So there's one called the capture screenshot. We have a document open in Microsoft Word. Then we have a window open in Google Chrome, threads versus processes. So in this specific situation, if you click on processes, in the first window, we have clicked on applications. So if you were to click on processes, you'd have something like this, the one shown on the second window. So you can see here we have chrome.exe appearing so many times. I think last week we discussed why that can happen. Maybe you have many tabs open or many windows open. So it depends on what you're doing on the internet. So each of them will have its own process identifier and the rest, as we discussed when you were doing the process control block. Okay. So this is just a recap from last week. And this is just what I've already explained. Now, when you're using the task manager, if you click on performance tab, we've clicked applications and processes. If we click on performance tab, it will actually give us the performance of our system. For instance, in this example, the CPU usage is 8%. You can zoom on your side if it's too small. Then we have the usage of the physical memory, the RAM. The RAM for this system is about 4 GB and about 2.2 is in use, as you can see from this. And then you can see from here, from this screenshot, this is where I'm interested. We have threads, because I want to introduce the concept of threads. So this particular operating system has 89 processes executing, and these 89 processes have 1,089 threads. The number of threads is usually more than the number of processes, as you're going to notice, but that's what I wanted to introduce, threads, because that's what I want to cover right now. These other sections for the memory I will cover in a different class because I haven't covered memory management. Now, if you click resource monitor here, this is what will be displayed on your screen. And you can see from here, the resource monitor just shows us the process identifier for different open processes and the status of these processes and how many threads are attached to each process. For instance, the first one, HP LaserJet service, the executable file, it has 23 threads attached to it. The second one has 18 threads and so on and so forth. So I wanted to concentrate on the section for threads. Threads are attached to processes. Okay. So I've given a link here that you can click on and read more about Task Manager and how to use it. Then we also have another tool called Process Explorer. It is almost like Windows Task Manager, but it's even better because it allows you to monitor your system perfectly. So for instance, it shows you all the files that are open and the directories attached to them. And it's free. You can just download it from the Microsoft website. Now, this screenshot that we have here is a screenshot for Process Explorer. So you can see here we have several processes here on the left. So if you right click on any of them, you'll see several options. And one of the options is kill process, and the other option is kill process tree. Those are the ones I'm concerned with. Now, what's the difference between the two? I think we've all used Windows Task Manager once or twice in our lives to end a process that is giving you a lot of problems. Maybe your computer is hanging, so you open Task Manager and then you kill a certain process or you end it. So what's the difference between killing a process and killing the process tree? You remember in the previous lectures, we had said that when you have a new process, usually we refer to it as a child process, and it usually has a parent process attached to it. So when you kill the process, you're only killing that specific process. You're not killing anything attached to it. But when you kill the process tree, it means you kill the process itself plus its parents. Or if it's a parent process, you also kill its children. So that means that you will not have any problem, because when you kill the whole tree, you're not going to have any issue, because if you kill a parent and you leave the child, that means you'll have an orphan process, which we discussed the other time. And an orphan process will still have a process identifier and might still use the system resources. So it's usually better to kill the whole process tree. So this is something you can do if you're using Process Explorer tool. This is still a screenshot of the same. Sorry, it's not very clear. Excuse me. So here, if you right click on any process again, you'll be able to see the thread identifier. At the top here, it's written TID. So thread identifier. So each process has its own threads. And for this specific process, chrome.exe, this one here, the one that is in gray, that's the one that has been right-clicked. So if you click on it, you're able to see its threads. And you can see each of the thread has a different identifier, just the way we talked about processes having different identifiers. So what is a thread from that brief introduction? Last week, we said a process can be thought of as a program in execution. Now, what is a thread? A thread is a unit of execution within a process. So a process can have from one thread to so many threads, depending on what that process is executing or what it is doing. So a thread is usually part of a process, while a process is a program in execution. I hope we understand that flow as we move along. So when you talk about multi-threading in operating systems, now that we've already said that thread is a unit of execution through the process code, and it has its own register, counter, and stack. Those ones are in memory. And you can have many threads within a process, like we have said. But these threads, look at this diagram. These threads usually have, they share the code, they share the data, they share the files. Now, this diagram is trying to explain the difference between a process that has a single thread and a process that maybe has 3 or more threads. So you can see in this first one where there's only one thread performing the task that is supposed to be performed. The code is here, we have the data and the files. And then because it is just one thread, it has its register, counter, and stack, which are found in memory. In this second example, we have a process, but it has 3 threads. So if you look at these 3 threads, they're able to share the code, they can share data and files because they're all based on one process, yeah? But you see they have different registers, counter, and stack, so that we don't really need to have them in the same, we don't have issues with the memory allocations, as we will discuss in memory management, I think in the next class or so. So that's the basic idea of having multi-threaded systems. Now, it's usually good for a process to have more than one thread. It makes execution faster because you're able to do many things at once. If you only have one thread, it can only do one thing at a time. But if you have 3, 4, 5, it means you're able to do 5 things at a time within the same process. There's another software called Process Threads View. Now, Process Threads View allows you to observe, and these ones are downloadable from the internet. They're free of charge. So if you had this software, Process Threads View, it allows you to view the processes and their threads. So like, for instance, in this diagram, if you were to click this green arrow, it would show you the processes that you have in your system. So if you click on any of them, it will show you the process identifiers. This is the first row, the name of the process and its path where it is based on. So if you want to see the thread associated with a press, you just click on the process from this screenshot, and then you'll be able to see. Like for instance, in this diagram, you can see we have clicked probably on chrome.exe, saying that because if you look at the title bar here, we have chrome.exe at the end of the path. So it means one of them was clicked here. Now, if we look at this, we have the threads, and all the threads have their thread ID. Then we have context switches. I don't know if you remember what a context switch is. We discussed it last week when we said when a process is running, sometimes it might need something, maybe input, output, or it might require something else. So it needs to leave the CPU area to get whatever it needs. So when it leaves that area, its state is usually saved so that when it comes back to running state, then the CPU is able to remember where it had reached with it. When you were discussing about the process states, you can have a process that is running and then it goes back to waiting. So when it goes back to waiting, you need to save its state so that when it comes back, the CPU is able to remember where it had reached with it. And that is what we call a context switch. So you can also see the number of context switches per thread. The last context switch column is also here, the status, and so on and so forth. There is a lot of information about them, but for now, I'm only concerned about the thread ID. Each thread has its own ID. Okay, so what are the benefits of multi-threading in a nutshell? Although I've already discussed a few of them, we can group them in 4 categories. The first benefit is responsiveness. Responsiveness means your program will continue running even if a part of it is blocked. What do we mean by this? If you're using a browser, let's say Google Chrome. Now this Google Chrome is a program or an application. So when you open it, it means it is now executing. So it is a process. So this process of Google Chrome, while it is executing, it can have several threads. There could be a thread that is used to display the web page. Another one is used for downloading, etc. So the difference is if you are using Google Chrome and it only supports single threading, what would be the difference? It would mean the thread that is responsible for displaying the web page, while it is active, then you're not able to do anything else. The thread for downloading cannot be active. So it means that the user has to wait for one task to complete before they go to the next task, because it is not multi-threading. So multi-threading will increase responsiveness to the user, because when you have many threads, you're able to do many things at a time, just like I explained using this diagram. When you have a single thread here, like for the example of Google Chrome, if one thread is for downloading information from the internet, when that thread is active, you can't do anything else because the system is single-threaded. But if it is multi-threaded, that means you have different threads performing different functions within the task. Then it means you're able to download at the same time you're viewing a web page, at the same time you're doing something else, depending on the number of threads that you have active. That is why we talk about responsiveness. The second advantage is resource sharing. Now, when we talk about resource sharing, we know that threads share memory and resources of the process which they belong, as I had shown in the other diagram. So when they share the code and the data, then you're able to have different threads within the same address space attached to the same process. The opposite would be each thread having its own resources. This would be resource intensive because it would mean you'd have to dedicate resources for each and every thread. So when they share the data, they share the files, then it means you only give out the resource to the process, and then all the threads attached to that process just share the resources. So it makes it much efficient. Number 3 is economy, and economy is related to resource sharing. This method is economic because of the resource sharing aspect. When you allocate memory and resources to a process, it is a costly process because when you have several processes executing, each of them has to have its own resources. So if you have threads within a process and each of them requires its own resources, it becomes uneconomical. So it's better when you have a process, and this process, the resources attached to it are shared by the threads that are attached to the process, rather than having each thread having its own resources. And that is why I'm saying economy comes from the resource sharing benefit. Okay. The last benefit is utilization in the multiprocessor architecture. Now, multiprocessor means you have more than one CPU running. So if you have more than one CPU running, if you're using a single threaded system, it would mean each process can only have a single thread. And if it has a single thread and you have a system which has 4 CPUs, but you're using processes that only use a single thread, you see, it doesn't make any sense because the other 3 CPUs will be idle as this one thread is active on one CPU. But when you have a multi-threading system, let's say your process has 4 threads or 3 threads. Each of these threads can be executed on any of those CPUs. So you see the execution will be faster. It will be much, much faster. If it was single threaded, you're only using one system. So it doesn't matter that you have 3 CPUs. So it's like you're wasting the other CPUs. So when you have a multiprocessor architecture, it's usually best to have a multi-threaded system so that you can have all the threads being active on either of the CPUs. And therefore it makes your system execute the tasks concurrently and more efficiently and obviously faster. Those are the 4 benefits of multi-threading. We have 2 types of threads, user level and kernel level. In our first and second lecture, I think we talked about user level and kernel level, the difference between the two, the user space and the kernel space. We said the user space, that's where the user interacts with the system, while the kernel space is the core of the operating system. And these two are very, very different. So when you have a user level thread, as you can see from this diagram, you have process P1 and process P2, and each of them has 3 threads. And these 3 threads are attached to a thread library. So in the user space, you have the threads running within the user space. When you talk about the kernel space, then it would mean the thread will be running in the kernel space and it would be controlled by the core of the operating system. So such a thread would be directly supported by the operating system. Unlike in user space, where the threads are controlled by the thread library, as you can see from this diagram. That's the only difference between the two, but the functioning is the same. It's the difference in who controls. Kernel level threads are directly supported directly by the OS, while user level threads are controlled using the thread library within the user space. So the difference between the two, user level threads are faster to create and manage, of course, because they're within the user space. Kernel level will be slower to create and manage because you have to access the core of the operating system. Number 2, user level implementation is by a thread library, like I've already said, while kernel level, this is directly supported by the operating system. Then we have user level threads are generic and can run on any operating system because they're within the user space. So it will not really matter whether you're using Windows 7, whether you're using Macintosh, whether you're using Linux, the threads will run because the thread library is generic. Then when we talk about kernel level threads, they're usually specific to the operating system because we know that a kernel is the core of an operating system and different kernels cannot be the same. The kernel of a certain OS cannot be the same as the kernel of another OS because that's the core of that operating system where we would have the commands and the rest. So it is specific to the operating system. And some operating systems actually combine user level and kernel level. A very good example is the operating system called Solaris. So it does a combination of the two. Next, I look at multi-threading models. You can see a message on my screen. My internet connection is unstable. I hope you did not lose me. Hope I am back. So multi-threading models, we have 3 types. We have many-to-many, many-to-one, and then one-to-one. And just from their names, that's where the difference comes in. We've talked about user space and kernel space threads. So when you have many-to-many, it just means many threads within the user space are multiplexed on many threads within the kernel space. So if you look at this diagram, we have 3 threads here and another 3 threads here in the user space. That means we have a total of 6 threads. Then if you look at the kernel space, we also have the same number, 6 threads. So it means many-to-many. If you have 6 here, you have 6 here. Many-to-many. If there are 4 here, you have 4 here. If there are 5 here, there are 5 here. So that you have many-to-many. Any number of user threads is multiplexed on an equal or smaller number of kernel threads. They don't always have to be the same. That is what it means. Many-to-one model is the second one. So from its name, we still have 6 threads in the user space. And then you can see in this case, it's very different from the first one, because in this specific case, we have the 3 threads being attached to one. many to one. In this one, you have many to many. So it can attach to either of them. But in this case, we have many attaching to one, many attaching to one. So many within a process are attached to one within the kernel space. Okay. And then we have one-to-one model. So this one will even be much easier to explain, where you have one thread in the user space multiplexing to one thread in the kernel space, as you can see from the diagram. The only problem with this method is that if you want to create a user thread, it has to be attached to a kernel thread. So a user kernel cannot exist without a kernel thread existing at the same time. So those are the three models of kernels that we have. Sorry, three models of multi-threading, sorry for that. With that, I'm done with part one of today, where we were looking at process management part two. Okay, now our second part for today is process synchronization. This is a technique used to coordinate the processes which use shared data. In an operating system, we have two types of processes, independent and cooperating. An independent process will not affect and is not affected by any other process as it executes, while a cooperating process is the opposite. It is affected or it affects other processes. So of course, when you talk about synchronization, we are specifically talking about cooperating processes, because independent processes may not need to synchronize as they are not affected by the other processes. So we want to look at 4 key terms: rest condition, critical section, semaphores, and busy waiting. These are very key terms when you talk about process synchronization. So I'll start with the critical section. A critical section, when you talk about operating system, is just a code segment where the shared variable can be accessed. Now, we also talk about something called an atomic action. So if you hear the term atomic action when you're talking about operating system, it just means that only one process can execute in its critical section at a time. Now, atomic operation is something that is done or not done, as in it can never be halfway done. If you start doing something, you have to finish it. So when we talk about a critical section, it's a code segment where if 2 processes or 3 processes need to access a certain shared resource or variable, then they have to share it from a specific area. So if they're getting it from a certain area, we call it the critical section. So it means you cannot have more than 1 processes accessing the critical section at the same time for obvious reasons. So when one is accessing the critical section, another one cannot access. It has to wait until the other one is done. So a critical section is a code segment where the shared variables can be accessed, and it is an atomic operation. It is never halfway done. So when it starts, it has to be finished. That means you can only have 1 process at a time in the critical section. The rest will have to wait. Now, this section in red is just to help us understand it from a programming point of view. Maybe as you're doing your programming units, maybe you do some coding, though I'm not going to do a lot of coding here. This is just to help us understand what a critical section is. So let's say you have a code like do entry section. Then you have the critical section where they are sharing the resources. They're accessing that resource. Once it has accessed the resource, it will exit from that section, then continue with the remaining parts. So it's just to help us understand the concept of what I have said, that when a process is executing, when it needs to access the critical section, it has to enter. Then it gains access to the critical section, then it exits, and then it continues with what it was doing before it came to the critical section. Okay. I'm going to cover entry and exit of critical section in just a minute. So I'm coming to that. Now, when you talk about the critical section again, it needs a solution to synchronize different processes. So it has to satisfy 3 conditions, the solution to the critical section. Remember, I've just talked about the fact that only 1 process can be in the critical section at a time. And why is that? It is because the critical section, this is where shared variables are accessed. So you cannot have 2 processes accessing a variable at the same time because it's a shared variable. Now, these conditions we have are 3. Number 1 is mutex, mutual exclusion. Number 2 is progress. Number 3 is bounded waiting. Now, what does all this mean? Mutual exclusion means One process can be inside the critical section at any time. That is what it means, only one at a time. So if anyone wants to get in, they have to wait. Let me use an example of visiting maybe a toilet. When you go to the toilet and you knock and someone is inside, you have to wait, you will not get in. So you have to wait until this person is done with the critical section and then they leave. Then now you can get in. Number two is progress. If a process is not using the critical section, it should stop. It should not stop any other process from accessing it. So let's say, let me use the example of the toilet again. If you have a toilet and there's someone inside it, they're not even using it. Maybe they're just there, maybe, I don't know, maybe they're just on their phone or something. And there's someone else who wants to use it. This person should not stop the other person from using it. That's what we are saying. So if you have a process in the operating system, it is not using the critical section, and another process wants to use the critical section, then this first process should not stop any other process from accessing it. That is what we call progress. So any process is allowed to enter the critical section if it is free. The last condition is bounded waiting. Bounded waiting means each process must have a limited waiting time to access the critical section. A process should not wait endlessly. So for instance, if you're waiting for the critical section, the process, there should be a certain time, a limit for the waiting time. Maybe it is 5 seconds, maybe it is 10 seconds, etc., that it is allowed to wait to avoid an endless loop of waiting. So I'll still use the example of the toilet. If you're waiting for someone to leave the toilet, there's a reasonable time you can wait, 5 minutes, 4 minutes. But you know, when it gets to 10 minutes, you'll be like, is the person inside really doing something, or have they just locked the door and maybe they have escaped, or maybe they've collapsed inside there, maybe they have fainted. You know, you start getting worried. So that is what we refer to as bounded waiting. A process has a limited waiting time to access that critical section. So the operating system must ensure that any process does not wait endlessly before it accesses the critical section. Number two, under synchronization, is rest condition. Now, this is a condition where you have several processes trying to access resources and modify shared data concurrently. And the outcome of the process will depend on the particular order of execution. So like, for instance, you have maybe 3 processes. They're trying to access a certain resource or a certain data. So if each of them is able to access that data and change them, each of them changes the data at the same time, it will lead to inconsistency. That is what we call a rest condition. So how do you avoid such a condition? This is where synchronization comes in. So you need to allow only one process to enter and manipulate data in the critical section. So I hope now it is clearer why we only need one process at a time, sorry, in the critical section. It is for synchronization. If you have 2 of them at the same time, they could both change the data at the same time, and then the output will depend on who changed it last. It's like if I log in, I'm trying to maybe look at your results or something like that, and then I see that your result is an A, and then I change it to a B, and then someone else logs in and changes it to a C. So the last person who changed it, hiyo ndio result yenye itabaki kwa system. So a rest condition would mean when I'm changing something, someone else should not be allowed to change it at the same time, specifically at the same time. Okay. Then number 3 is the semaphore. Now, a semaphore is just a variable, which is usually non-negative and is shared between threads. A semaphore just helps us in signaling, yeah? So it helps us when we are doing the synchronization. And what do we mean by this? Let me just scroll here. A semaphore can either allow or disallow access to a resource. So it will either give you permission or it will deny you access to a resource, which is in the critical section. You remember when I was discussing critical section, I said I'm going to discuss entry and exit in just a bit. When you have the critical section, we have the entry, you access the critical section, then you exit. So I want to discuss the entry and the exit. What are they? So entry and exit are 2 operations. Entry means you want to access the area. Exit means you've already accessed, you want to leave. It's like when you enter a toilet and after you're done with whatever you're doing, you leave, you exit. So we have 2 operations. Wait operation, which we also call the P operation. Now this is used to control entry into the critical section. Then you have the signal operation, which we call the V operation, which is used to control exit. Once a task is done with whatever it was doing in the critical section, as it leaves, it will call the signal operation. So what is this wait operation? Now, if the value of the weight is positive, then the value of the weight argument S is decremented. Now, what do we mean by this? Let me use the example of the toilet. I'm sorry, I have to use the toilet to help us understand the concept. If you're in line waiting to use a toilet. Now, how do you know that the toilet will be ready for you to get in? That is where the wait operation comes in. So if there are 4 people in front of you, that means maybe your weight value is 4. So here we've written, if the value of the weight is positive, so in this case, you're waiting 4 people are ahead of you, then the value of the weight argument S is decremented. So mtu mmoja akiingia kwa entry, then we decrement the value. Now there'll be 3 people in the line. If 1 more person enters the toilet, now there'll be 2 people. So we keep decreasing until it reaches 0. That means you're the next one. So now you're able to enter. I hope that explanation will help you understand. So like if you're waiting to get into a toilet and there are 4 people in front of you, 4 is the value of our semaphore. And so we are going to decrease the value then that we represent by S over here. So you're going to wait. If 4 people are in front of you, mmoja akiingia kwa your critical section ama kwa toilet, then it means now you're left with 3 people. If someone else gets in, now you're left with 2 people, and so on and so forth until it is 0. So when it is 0, it means you're next in line, so you're able to enter. So when you enter and you perform whatever you're doing in the critical section, if you want to leave, then you call the signal operation. The signal operation is also called the V operation, and it controls how you exit from the critical section. So it removes one process from the list of waiting processes and then awakens that process. It awakens the process. So it increments the value of its argument S. So in such a case, once you have left the critical section, you're inside, you're performing your task and you're done. So you call the signal operations. If you're saying, yo, I am finished with what I'm doing, so I want to leave the critical section for someone else. So when you leave, the process that was waiting in line, let me use the example of the toilet again. If you're done with the toilet na umetoka, huyo mwenye alikuwa next in line sasa, anaamshwa. Let me use that term, is awakened. So anaamshwa alafu anaingia. So meaning there's someone else entering the critical section, and that's why we increment the value. I hope you've understood the difference between the two. Wait is for entry, signal is for exit. Then the last term that we were talking about was busy waiting. What is busy waiting? Now we've already mentioned it a bit. Remember we have said, when you're trying to access the critical section, we don't want to have a process that waits too long to access the area. So we talked about mutual exclusion, where we said if one process is in the critical section, the others must wait. So as they wait, how will they know? How will they know that it is their time to get into the critical section? So it keeps checking. It's like when you're in the queue to join the toilet, you keep on knocking, you keep on knocking. So una knock na unangoja, una knock na unangoja. Mtu atoki. So you keep knocking, you keep waiting, you keep knocking, you keep waiting. That's what we call busy waiting. So busy waiting is a technique in which a process repeatedly checks to see if a condition is true. Is the keyboard input there? Is a lock available and things like that? So like in the case of the toilet, you're knocking to see whether there's someone inside. You knock again, is someone inside, you know, and stuff like that. So you keep checking, you do it repeatedly. So you're busy waiting. You're waiting, but you're busy because you keep checking whether the critical section is available. Okay, so process synchronization can be handled in 2 approaches. We have software and the hardware approach, where you synchronize your hardware. Now I'm going to discuss a few of these process synchronization algorithms. The first one is disabling interrupts, how you can deal with synchronization. Disabling interrupts. I think in the first lecture when I was talking about functions of operating systems, one of them was interrupt handling. And I remember telling you that an interrupt is a break in the normal process, yeah? Like when you're using a system and then you just see something on the screen, maybe someone attaches a USB device, and so something comes on your screen telling you there's a USB that has been attached, what would you like to do? So that's an example of an interrupt. So you can have your interrupts disabled in the system, yeah? It's a very easy thing to implement, yeah? But the problem is that when you disable interrupts, no other process is allowed to perform a context switch operation. You remember we said context switch means if something was running, if a process was running, then maybe it's blocked. Maybe it needs an input or an output or something. So inatolewa kwa line, ingine inaendelea. So ikipata chenye inataka inarudi kwa line. So you see, if you disable interrupts, this other process will not be able to go back to the line because it will not be allowed to interrupt. That's the only problem with disabling interrupts. Number two, the second type of algorithm is the lock variable. Now it's very simple here. Lock variable just means you have a lock and unlock technique. If a process wants to enter the critical section, it will check whether the door is locked. That's what we call the test lock. So the lock will be set as 0. So if the lock is 0, it means the door is not locked. The process can enter the critical section, and then when it locks the door, it will set it to 1. So if the lock is 1, it means it is locked and there's a process inside in the critical section. So it has to wait until it becomes 0. A very simple concept that when you want to enter the critical section, if the algorithm in use is lock variable, it means the process will check the value on the door. Is it 0 or 1? If the value is 0, it means that the critical section is free. So it's able to access the critical section. So immediately it enters, it locks the door, and then the value is set to 1. So if anyone else comes checking, then they'll know there's someone inside who is still in the critical section. So when it leaves, then it will turn back to 0 so that another process can get into the critical section. Basically, that's the idea with the lock variable. So as you can see in this diagram, while lock is not 0, it means the lock is 1. So when the lock is 1, it means that the door has been locked. So you're able to do whatever you want to do in the critical section. Ukitoka, lock inakuwa 0. So mtu mwingine anaweza ingia. So when another process gets in, then the lock is set as 1. So when it is set as 1, you're able to be in the critical section, do whatever you want. When you're done with the critical section, the process leaves and the lock is set as 0, and so on and so forth, and so on and so forth. Now, the only problem, challenge with this algorithm is what we call a spin lock. A spin lock is a lock which causes a thread trying to acquire it to simply wait in a loop. So it will keep on checking, is the lock 0, is the lock 0, is the lock 0? What if the process that is inside the critical section is performing a really huge task, you know? And so it stays there for a very long time. So these other processes will keep on checking. Spin lock, it checks whether the lock is available, it's not available. It checks again, it's not available. Checks again, it's not available. So that's what we call a spin lock. Another thing, you can also have two processes at the same time. For instance, here the lock is, if I want to get into the critical section, you have process 1, you have process 2. If we both check at the same time na tuone ni 0 na sisi wote tuingie ndani, it's very possible, by the way. So the two of us get inside before one of the processes has a chance to lock it to 1. We've already entered the critical section. So two of us are in the critical section. So you see, that's going to be a problem. That's going to be a problem because each of us has the key to enter the room. So this lock variable, that specific issue I've talked about, having two processes accessing the room at the same time, is solved using the test and set lock. Here we just have lock variable. Is the lock variable 0? Okay, let me get in. But what if another process is checking also at the same time? So the both of you will get in, then what happens now? We might have a deadlock and things like that, or a race condition. So in order to avoid that, we have the third algorithm called test and set lock. Now the only difference here is in the set and in the testing. So in this case, you test and then you set. You test first. Is anyone else also checking at the same time? No, let me lock. So that makes it better than the previous one. So it only allows one process to read and change the value in an atomic way. Remember, we said atomic means only one at a time, only one at a time. So that means you cannot have the problem we have with this other algorithm, where two processes can check at the same time and they both acquire the lock accidentally. The last algorithm is called Peterson's solution. It is also used in synchronization, but it is only used for two processes. If you have more than that, it will not work. So how does it work? It uses what we call shared memory. Now, it has two variables. One is called the flag, and the other one is called the turn. Now, the flag variable is a Boolean. Boolean means true or false. I think we know that from the programming. And then we have the turn variable that is used to store the process states, which we discussed last week. So If the Boolean value is true, that means if the flag is true, it means that the process wants to enter the critical section. So the turn variable is actually a lock. The value of the turn variable must be equal to the process identifier. Let's not get lost. So we're saying in this case, it uses something called a flag. So if the flag is true, it means it's able to access the critical section. But it can only access the critical section if its process identifier is equal to the turn variable. The turn variable is also a value, and that value must be the same as the PID of the process. So the turn variable, ikiwa na identifier, like let's say if my ID is 2528, if I want to access the critical section, the critical section there's a turn variable attached to the Peterson solution. So this turn variable must also display 2528. It's like in the bank, when you go to the bank, how do you know you're the next one to be served? Your ticket number will be displayed on the screen. So you will only go there if your ticket number is the same as the one displayed. So it's the same concept here. If your flag is true, it means you're able to access the critical. But in order to access the critical, the process identifier of that process must be the same as the turn variable, just like I've explained. Ukienda kwa bank and you want to access the counter, your ticket number must be displayed there for you to be able to be served. So they have to be the same. If you go there with a different ticket number, then it means you're interfering with the flow of things in the bank. Okay. So to explain that, I can use this diagram here, where we have start. So we have two processes, process A and process B. So we've talked about the flag and the turn. We have said the turn variable contains the process identifier, while the flag can either be true or false. So if it is true, it means that that flag is able to, not that flag, if it is true, it means that that process is able to access the critical section. True is also the same as 1, false is the same as 0. So let me start with this side. So we have process A. So we're checking the turn. Is it process A? Is it process B? So it will check whether the process identifier is the same. So if it is process A's turn, it will check, do you have the flag so that you can access the critical section? 1 means yes or true. So if you have the flag, then it means it is the turn of process B, access the critical section. And when it is done, process A will come in and then it will end. So it's the same thing on this other side. If the turn is for process B, then we check process A's flag. Now, if process A's flag is 1, then it means that is true. So A will be allowed to access the critical section. And then when it is done, then we will have process B coming in, then it will end. Still coming back here, we check turn, process B. What if process A's flag is false? That means process A is not ready to access the critical section. Then it means it is the turn for process B. So it will do whatever it's doing and then it will end. Same case here. If we check the turn for process A, then we check the flag for process B. But the flag is not true, meaning it is not ready to access the critical section. So it means that process A will be allowed to access the critical section, yeah? And then it ends. So when you'll be going through the notes, this will make much more sense to you. Okay. Then we have something called the mutex lock. That's another algorithm. I've already talked about mutual exclusion. So here I'm just going to briefly mention a few things here and there. In the entry section, you have a lock. So when you have that lock, you're able to access whatever resource you need. And once you're done, you release the lock. That's a basic idea of mutex, a mutex lock. So if you want to access something, you're given a lock. After you're done with what you're doing in the critical section, you release that lock. As simple as that. It's like when you enter a toilet na unafunga mlango, na ukitoka unafungua mlango. So in operating system, we refer to it as a lock. You lock so that you have mutual exclusion. Once you're done with the exit section, then you release the lock for another process. Okay. Now, we've discussed process synchronization, we have looked at algorithms, but still we have problems with process synchronization, and we group them into 3. The first one is called bounded buffer, or rather producer-consumer problem. I'll use the diagram to explain. In such a case, you have a buffer which has several slots. Now, these slots can store data. Then you have the producer whose function is to generate data and put it in the buffer, while the consumer takes the data from the buffer and consumes it. So the producer generates data, puts it in the buffer, while the consumer picks the data from here and consumes it. Now, what's the problem? Why is this a problem? This is a problem because if a producer tries to enter data into the buffer, and at the same time, you have the consumer also removing data at the same time, then it's going to be a little tricky if they're both doing it at the same time. So they need to be synchronized. Also, a producer can try to insert data into an empty slot of the buffer, and then the consumer tries to remove that data from a filled slot in the buffer. For instance, what if this buffer is empty and this one is full? And then the producer is inserting into the empty one, and the consumer is trying to get the data from this one here, where the producer is also inserting at the same time. So that is what brings a problem. So the two processes will not produce the expected output if they run concurrently. So we need to make the producer and the consumer work in an independent manner. When you're adding data and when you're getting that data out, those two processes should not happen at the same time. That's what we are saying. So when data is being added, the one that is getting the data should wait. Then when the one adding the data is done, then the other person can come in and then they get the data. Let's use an example here, where here we have a producer who's producing some food for this person to eat. So when this producer has the food ready, he receives a notification. The consumer receives a notification, food is ready. So you're able to put the food here. So after they've eaten the food, they also give a notification to the producer that food is eaten. So notification is a very good way to work with this. So like in this case, if the producer is trying to put data here and all the buffers are full, then the producer can notify the consumer that I have nowhere to put my data. The consumer also at the same time might be trying to get data from the buffer, but maybe the producer has not put anything. So the consumer can send a notification to the producer. There is nothing to fetch from the buffer. So notification is a very good way to solve this issue. So in such a case, it means if we did not have the notification here, this person would just keep adding food, adding food, adding food, and they may not even know whether this person is eating the food or not. They just keep adding it and adding it and adding it. And of course, that will bring wastage and loss of resources. So you can see in this case, another way to solve it is by using the mutual exclusion, where when the producer wants to give the consumer the data or the food, they have like this box over here where there's mutual access, yeah, a mutex access. So the food is put here, then the consumer comes and gets it from here. So it's only one thing at a time. It's either the food is being put or the food is being taken out. So you cannot have both of them being done at the same time. Okay. The second problem is called dining philosopher's problem. Dining philosopher's problem. Now, let's look at the diagram. I have two diagrams here. We have 1, 2, 3, 4, 5, 6. In the second diagram, I have 6 philosophers. We know that philosophers are people who like to think. So we have 6 philosophers, and these philosophers, they're only allowed to eat or think. So when you want to eat, you must use 2 chopsticks. So you can see for these philosophers, there's one on your right and there's one on your left. So you have to pick one on the right and one on the left. Obviously, if this person picks, this other person will not have one of them because unafaa ukue na mbili. So if I take the one on my right and the one on my left, it means the person next to me will not have this one here. So he'll be missing one, he'll not be able to eat. That is what we call the dining philosopher's problem. So what exactly does it mean? It involves allocation of limited resources to a group of processes in a way that you avoid a deadlock and a starvation. I'm covering deadlock and starvation in about 5 minutes. So I'll explain that then. So you have a number of philosophers seated around a table with one chopstick between each pair of philosophers. So they can only eat if they pick up the 2 chopsticks adjacent to them, like I have said. So obviously, if they pick the 2, it means the one next to them will not have one. And if they all try to pick them at the same time, again, it will also lead to issues. There'd be a deadlock. Because if I pick this and we are both struggling for this one, then it will be a deadlock. If you have 2 processes struggling to pick a certain resource, none of them wants to let go of the other. So there'll be a deadlock in the system. And that's what we refer to as a dining philosopher's problem. So usually there's an algorithm where, for instance, you can have something like this. The philosopher is allowed to think until the left chopstick is available. When it is, pick it up. So like in this case, let's say these are the philosophers, yeah? This is the left chopstick. So each of them will pick the left chopstick. No problem there. Then they pick the right chopstick, as you can see from here, when it is available. But now you see that's where the problems will come, because you'll have to keep waiting. If you pick the right one and you want to pick the left one, if the other person picks it faster than you, then you're going to be left without a chopstick and you'll not be able to eat. That is what it is. So it will most likely result in a deadlock. I'm going to discuss deadlock in a bit, then maybe this will make more sense to you. And starvation, I'm discussing them in just a bit. Okay, so again, that can also be solved using mutual exclusion, where if you want to have an access to a resource, then we have mutual exclusion, an atomic operation where you only have one person at a time, one process at a time, accessing the resource. The last problem is called readers writers problem. Let me use the diagram. We have processes that read data, and we have processes that write data. Reading means you're just accessing, you don't change anything. Writing means you're modifying data. So when you talk about process synchronization, we don't want a situation where someone is reading data, but at the same time, there is a process that is writing the data, changing the data. So it will bring a problem. Because if I'm reading something and someone is changing it at the same time, imagine you're on a certain web page, and as you're reading the information, it keeps changing because the programmer is working in the background, making some changes. So you see, it will bring a lot of confusion. So it's usually better than when they want to make changes, they do it when someone is not able to access the website. And that's why if you try to access the website when they're doing changes, it will tell you website not available because they're still writing, they're making some changes. So this is also the solution you can use here. Make sure that when a writer is accessing a resource or accessing a certain process, then a reader is not accessing it and another writer is not also accessing it, so that you can have synchronization of the processes, exclusive access to objects. That is what it means. Okay, part 3 is IPC, very short. IPC means interprocess communication. And how can we have processes communicating? Number 1 is message passing, where you have processes passing messages to each other, where you have send message, receive message. I'm coming to that in a bit. We also have something called pipes. Pipe is used to communicate between two processes, and it is usually half duplex in nature, meaning the first process communicates with the second. So if the second one wants to communicate with the first one again, it creates another pipe. It creates another pipe. So a pipe is usually one way. If I want to communicate, child A wants to communicate with B, it creates a pipe. B wants to communicate with A, it creates another pipe, and so on and so forth. The third method is FIFO, first in, first out. Now this is communication between two unrelated processes, and it is full duplex in nature, meaning when the first process communicates with the second, then the second one can also communicate with the first one. It doesn't need to create another channel. Message queues. A message queue allows for communication between processes with full duplex. So how do they communicate? A message will be posted somewhere, and then it will be retrieved from a certain queue. So it gets a message from the queue. I'm also going to discuss that in a bit. Once retrieved, the message is no longer available in the queue. It's like when you have inboxes in your email or a message in your inbox. Once you read the message, it is no longer in a queue because umeshaisoma. But if someone sends you an SMS and you don't read it, and another one comes in from someone else, and another one comes in, you'll see that the counter keeps increasing. You have 20 messages. Once you read them, as you read one, the counter reduces to 19, 18, 17, so the queue reduces. Shared memory, I'm also discussing that in a bit, where we have processes communicating through a section of memory where they share, and then direct and indirect communication. Direct communication means you need to know the names of each of the processes as they communicate, and only one link is used. But in indirect, you can use a mailbox, a common mailbox, where each process is able to share communication links. But I'm discussing that in a bit. So out of this, I want to discuss a few of them, like I've said. I'll start with shared memory. I'll use the diagrams. So you can see here we have process A and then process B. Now look at the blue arrows. They're all coming and going to shared memory. So this process B is getting something from shared memory, nakuja huku. Process A is depositing something in shared memory, then process B picks it. So they're only able to communicate through the shared memory section. Another way of doing shared memory is using the kernel. where anything they need to exchange is shared at the kernel level. So they just fetch the information from there or they drop it there. Message passing, which we have talked about, we deal with sending messages and receiving messages, as simple as that. A message usually has two parts. You have the header and the body. The header has the type, source identification, destination identification, etc., while the body contains the actual message. So if process A is sending a message to process B, it uses the send call. Then the receiver will receive it using the receive call. As simple as that. So here, this is where we talk about direct and indirect communication. So indirect communication, the two names, if this is process A and this is process B, they need to know each other's names. So you can see here it is written send B message, receive A message. This means process A is sending a message to process B. Then this means process A is receiving a message. You know, that is what it means. So they need to know each other's names, A and B. When we come to asymmetric, now that is called symmetric. Asymmetric means I don't need to indicate the receiver of the message or the sender because I know them. Only the sender will name the receiver. So if process A is sending to process B, then he will write send B message. Only the sender names the receiver. There's no need for the receiver to name the sender. So you can see here it is receive message. It doesn't name A, like in this other case. That's the difference between symmetric and asymmetric. In indirect addressing, we have something called a mailbox. So when you want to send a message to a process, all these messages are put in something called a mailbox, and then the receiver will come and pick the message from the mailbox. That is what it means. And of course, you have different types of links: one-to-one, many-to-one, one-to-many, and many-to-many, just like when you're discussing the threading. So it's just the same concept. One-to-one means one sender can only communicate with one receiver, so you only need one link. Many-to-ones, you have many senders communicating to a single receiver. One-to-many, you have one sender communicating with multiple receivers. Like I can send a message to all of you via your emails. That's one-to-many. So there'll be, I'll be broadcasting a message. Many-to-many means multiple senders want to communicate with multiple receivers. Then finally, you have the benefits of IPC. It allows for information sharing. Why do processes need to communicate? Efficient resource sharing. It increases communication speed, and also modularity, where you have the architecture broken down and the modules are able to cooperate, so there'll be efficiency. Okay, hope that section clear. The final part is deadlocks and starvation, which will just take us like 5 minutes. Now, what is a deadlock? Yes, what is starvation? Mike Humphrey, you're disrupting our class. Okay, so concurrency, we have deadlocks and starvation. What is a deadlock and what is starvation? Deadlock, let me use a practical example. If I have a pen and my friend has a paper, I don't have a paper and he doesn't have a pen. Let me repeat. I have a pen, my friend has a paper. I have a pen, but I don't have a paper. My friend has a paper, but she doesn't have a pen. And we need to write something. Now, if I refuse to give my pen to my friend and he refuses to give me the pen, then it means we cannot do anything. That is what it means. That is what we refer to as a deadlock. I have a resource, but this resource, I don't want to share it with other processes. So these other processes are not able to do anything because there is a process, there is a resource they require from me and I'm not releasing it. That is what we call a deadlock in operating systems. On the other hand, starvation basically means the system keeps checking for priority. Different processes have different priorities, like we discussed last week. So if a process has a high priority, inashinda inapatiwa hizo resources. It's given the resources to use all the time, while a process that has a low priority never gets access to such resources. That is what we call starvation. So if you look at this diagram, we have process 1 and process 2. Process 1 has resource 1. Process 2 has resource 2. Now, process 1 might want a resource which is held by process 2, but process 2 doesn't want to give it out. So nothing is happening. That is what we call a deadlock. Okay. For a deadlock to happen, we have 4 conditions. We call them the Kaufman conditions. Number 1 is mutual exclusion. I think I've talked about mutual exclusion so much. There should be a resource that can be held by one process at a time, one at a time. So process 1 is allocated resource 1, and that resource cannot be given to another one. That is what we call mutual exclusion. A resource that can be held by one process at a time. Hold and wait is the second condition under Kaufman conditions. Hold and wait means a process can hold multiple resources and still it can request for more resources. So like in this example, process 1 has been allocated resource 1, but it is requesting, process 2 is requesting for the same resource 1, yet it is allocated resource 2 and 3. So process 2 iko na resource 2, iko na resource 3, but inaitisha resource 1 yenye iko kwa process 1. So that is what we call hold and wait. You're holding and you're waiting for another one. The third one is no preemption, which I also mentioned last week, the meaning of preemption. A resource cannot be preempted from a process forcefully. So what do we mean? If this is process 1, it has resource 1 allocated to it. Now process 2 is allocated resource 2, but it is requesting for resource 1. So no preemption means that this resource cannot be preempted forcefully. That just because it is requesting ati itapatiwa, no, it cannot be done forcefully. It has to wait for the operating system to give it out. So it has to be voluntary. And then the last condition is what we call the circular wait. Circular wait means a process is waiting for a resource held by a second process, which is waiting for a resource held by the third process, and so on and so forth. So like in our diagram, process 1 has been allocated a resource 1, as you can see here. This is process 1, imepatiwa resource 1. But at the same time, process 2, which has been given resource 2, is also waiting for another resource. So you can see it's going round in a loop. Resource 1 iko kwa process 1, but process 2 is also waiting for it. Resource 2 has been assigned to process 2, but process 1 is also waiting for it. So I'm waiting for something that someone else is also waiting for, someone else is also waiting for. So that is what we refer to as a circular wait. Those are the 4 conditions for a deadlock to occur. They're called Kaufman. Mutual exclusion, hold and wait, no preemption, and circular wait. Those are the 4 conditions. Finally, we have starvation. Now, what is starvation? I've already talked about what it is, where we look at the priority of a process. If its priority is high, then it will be given a resource to use. If the priority is low, it will not be given the resource. So in such a case, kazi inaendelea, lakini mwenye akona priority ya chini, anangoja kabisa, anangoja. So we can solve the issue of starvation using something called edging. Now, edging means you keep increasing the priority of a process which has been waiting for a long time. That is what we call edging. So if a certain process has been waiting to access a resource and it's not able to access it because maybe it has a low priority, what the operating system does, it keeps increasing its priority mpaka ifike huko juu so that it is able to have the resource. So here we have a table showing the differences between deadlock and starvation. I hope you will not have any troubles here because I have explained both of them. Maybe just the third one. Deadlock is often called a circular wait because kila mtu anangoja. Starvation is called a live lock. Why is it called a live lock? It's a live lock because kazi inaendelea, lakini mimi sipati resources because my priority is low. So I am locked, but it is live. As in live, kazi inaendelea. So only the processes that have a high priority ndio zina benefit. But those that have a low priority, they keep waiting. Okay. Now, how do you deal with a deadlock? We have deadlock detection. We make sure it detects the deadlock in advance. We have deadlock prevention. Prevention, of course, is better so that you're not able to have the deadlocks in future. Prevent it before it can occur. The operating system can prevent the same. Then you have deadlock avoidance. You can also avoid a deadlock from occurring. The operating system can do the same. Like it has something called the wait for graph, where it allocates a time for resources to be given out and things like that, so that you avoid a deadlock situation. Now this last section is just explaining a few terms that we have already covered here and there. Messages. Sorry for that, hope I am back. Okay, so we have messages. Messages means you have a block of bytes with an accompanying type. Like for instance, in Unix, we have message send and message receive system calls, which are used for sending and receiving messages, like we've already talked about. Then, sorry, I'm hotspotting my phone and someone was calling. Okay, hope I'm back. Sorry, I was hotspotting on my phone. I'm just about to finish. Let me check someone has unmuted. Okay. Then you have semaphores, which you've already talked about. These are values that are used to help us with synchronization as signals. We talked about the wait semaphore and the other semaphore that is used for the entry operation and the one for the exit operation. And then we've talked about signals. It's just a mechanism that is used to inform on the occurrence of events that are happening within a system. And we have different types of signals in operating systems. Now, I don't expect you to cram anything here, but just for your own knowledge. For instance, in Unix operating system, there's a signal called SIG-HUP. So it means hang up. We have SIG-INT for interrupts and so on and so forth. So this is just for your own knowledge. Then atomic operation, which I've already said what it is, where you have an operation executing without interruption. So you have one operation at a time. Like if you're using critical section, only one process is allowed at a time. We've also talked about the spin locks, which can be acquired by one thread at a time so that it will keep on checking whether it is able to acquire a lock so that it gets into the critical section. And that should mark the end of today's lecture. Okay, let me stop the recording.